In Unit 4, we're going to focus on systems of equations, so basically meaning two or more equations at a time. So we'll focus on how to solve systems graphically and algebraically, and then we'll also talk about systems of inequalities, how to solve those graphically, and then also applications with both. So the first lesson here is focusing on solving linear systems graphically. So again, definition of a system is whenever you have two linear equations at the same time. It's called a system of equations. Both of these equations will be in two variables and have graphs that are straight lines. So here's just two examples of systems. So we have x plus y equals 3, 3x plus 4y equals 2. So basically we just have these two equations. Same with this, two linear equations. So first thing in this lesson is we're going to focus on how to solve a system of equations graphically. So there's going to be three different scenarios that we can come across. So if I have my x and y axis, the first and most common solution is whenever your two lines, so I have a line here and I have this line over here. So I would graph my two separate equations. They would be given to me by some equation, and the first scenario is whenever you have one solution, meaning the lines are crossing in one spot. So this would be a one solution case. So that's where the two lines cross in exactly one spot. Another scenario that we could have, so let me start with my x and y axes again. Would be a case where I have a line and then I have a second line and they never cross. So this situation, since they never cross, would mean that there's no solution. And this is going to occur whenever the lines are parallel to each other. And if you remember from the last unit, parallel lines have the same slope. So if we ever get values where the number in front of x is the same, that means the lines are parallel, which means that there would be no solution to the system. If you remember too, when we're looking at the graph of a line, that represents all solutions or all x and y values that satisfy that equation. So when we're talking about a system, now you're trying to find all x and y values that satisfy both lines at the same time. So in this first example, we had one solution. This is the only point where there's an x and y value that works in both equations. The second situation, there's no x and y value that works in both equations at the same time, which is why they never cross. And then the last scenario is what happens if you get one equation, you graph it, so you get this graph, and then you get your second equation and it ends up being exactly on the line. So it ends up being the same equation. In this case, every single point along both of these lines is going to be a solution to the system. Every single point, every single x and y value will work in both equations. So this would be a case of infinite solutions. So infinite. So these are going to be our three scenarios. Again, the first one's the most common when your graph intersects once, but it is possible for the lines never to cross or to cross in infinitely many places. So let's go ahead and try some examples now that you see the different situations. So the steps here for solving, you're going to be given an example. So look at example 1. We have two equations. Step 1 is to graph the first equation. So I'm going to just call this equation 1. Doesn't matter which one you choose to graph first. But if you remember from last unit, we talked about how to graph lines. So you always have to get it into y equals mx plus b form first. So we have y equals negative x plus 4. And in the last unit, we did talk about some different ways. Remember, you could graph an equation by plotting points. You could graph an equation by its x and y intercepts. I'm going to use the slope-intercept form and graph by using the slope and the y-intercept. So my slope here is going to be -1. So that tells me down 1 to the right 1. And my y-intercept is going to be 4. So that means I'm going to start up at 4, and I'm going to travel down 1, right 1, down 1, right 1. You're going to keep doing that until you've covered the entire graph. Then you're going to backtrack and go left 1, up 1. Once you have your points plotted, go ahead and connect your line. And then we'll get our arrows on there and go ahead and label it. So x plus y equals 4. Okay, so then I'm going to repeat the process with my second equation. Step 2 says graph the second line. So my second equation is x minus y equals -2. So I'm going to go ahead and I'm going to get this into y equals form. So subtract x. I have -y equals -x minus 2. Divide everything by -1 to get y by itself. So we have y equals positive x, because negative divided by negative is positive, plus 2. So that tells me the number in front of x is 1, so my slope is going to be up 1, right 1. And then my y-intercept is going to be the positive 2. The number at the end. So I'm going to start at 2. So start at 2, and we're going to travel up 1, right 1, up 1, right 1, up 1, right 1, and then, go to the backtrack, go to the left, and then go ahead and connect those points. Get your arrows on your line. And you can label it x minus y equals -2. And then we're looking for the solution. So this is going to be a case our lines cross in exactly one spot. So my solution is going to be this x and y value where the lines intersect. So this is the solution. And you're going to state it as a coordinate. It's the x and y values that work in both equations. So 1, 3 is this coordinate. So then that would be my answer. So the solution is 1, 3. Make sure you guys write these as coordinates because they are x and y values. They are ordered pairs. Now, if you wanted to check this solution, what you would do is you would take 1, 3 and you would plug it into both equations. So just to kind of show you roughly what I would do to check. So I would take my 1 and my 3, I plug them in for x and y, and you see, does it really work? Well, 1 plus 3 is 4, so yes, it does work when I check it. Then over here, I would do 1 minus 3, which does give me -2, so it works. So you don't have to show the check, but make sure you do know how to check so that you're checking your work on a test in your calculator in your head. So let's look at some other examples. Example 2. Let's solve these by graphing. So let's go ahead and we will start by solving each equation into y equals mx plus b form. So I have -2x plus 2y equals 8. So I'm going to add 2x over to both sides. So I have 2y equals 2x plus 8. Divide everything by 2. So y equals x plus 4. So slope is 1. The number in front of x is 1. Y-intercept is 4. So start up at 4. And then I'm going to travel up 1, right 1. And then you're going to backtrack. Then go ahead and connect your lines or your points and put your arrows, your label, all of the things that we always need to do when we graph. So negative 2x plus 2y equals 8. And then I'm going to take my second equation. I'm going to solve that. So I'm going to do that. Let me just erase what I have here. Okay, so my second equation is 3x minus 3y equals negative 6. So I'm going to subtract 3x from both sides. So subtracting 3x, so I have negative 3y equals negative 3x minus 6. Divide everything by negative 3 to get y by itself. So I have y equals x plus 2. Slope is 1, y-intercept is 2. Now you might be thinking, if you remember the last one, my slope was also 1, I just had a different y-intercept. So that should kind of stand out to you, as this is going to be a case where we have parallel lines. So my y-intercept's at 2, and I'm going to go up 1, right 1, up 1, right 1 for my slope. And you can see that these lines have the same slope, so they are parallel, which really means that they will never intersect. So when I graph this, I'm going to go ahead and connect it, get my arrows on it. But then my solution is going to just be that there is no solution, because the lines never cross. They don't have any common points or any common x and y values that satisfy both equations. So this is a no solution case. So that's it for that one. Let's look at one last example. So again, we're going to start it off the same way. So I have 3x plus 3y equals 12. Get the y by itself. So divide everything by 3. Y equals negative x plus 4. So slope negative 1, y-intercept is 4. Start up at 4. Down 1, right 1. Down 1, right 1, because it's a negative 1. We'll go down, and we always start by going to the right, and then we do the opposite. So go ahead and connect your points, get your line. So we have 3x plus 3y equals 12 for this equation. And then we're going to go ahead and we're going to do the second one. So the second equation, we had negative 6x equals 6y minus 24. So let's go ahead, and we got to get y by itself. So this time y is on the right hand side, so let's bring the 24 over first. So we have negative 6x plus 24 equals 6y. Again, get y by itself. So divide everything by 6. So we have negative x plus 4 equals y, which, remember, is the same thing as y equals negative x plus 4. So my slope is negative 1. My y-intercept is 4. And you might be thinking, well, wait, I just graphed this equation. So y equals negative x plus 4, we got the same equation. So if you get the same exact equation, and if I go up to my graph and I start with a y-intercept of 4 and travel down 1, right 1, I get the same line. So since I get the same line, that really means that every solution in this first equation is a solution in this second equation. So this graph is exactly the same, so I could actually just label it. I don't need to redraw the line. And that means that every single solution on this line is a solution in both equations. So that means there's infinitely many solutions. So infinite solutions. And that's the last scenario. So just keep in mind, infinite solutions are going to occur whenever you get the exact same line. Parallel lines are going to occur when the slopes are the same. Remember, both of these equations in this previous example had the same slope. And then if you don't have any situations where you either get the same equation or same slope, you just have two completely different equations, the lines will cross in some place.